Welcome back. So we're going to continue talking about geometry and specifically level one of gaining a geometric understanding. So analytically understanding geometric shapes. And when analyzing at this level, we want to look at components and characteristics of the shape. So how many components does it have? Like how many sides? What's the relationship between these components? So say, are the lengths all the same? Their relative size, orientation, and their symmetry. So these are all factors that are going to now come in at level one that may have not appeared for students at level 0. So the first thing we want to talk about before kind of diving into more details about level 1 is one of the things that shows up here is symmetry. And so there are 2 ways we can identify symmetry. And the first type of symmetry we have is called reflection symmetry. And here, in this case, there is a line that can be folded over, so half the figure matches with the other half perfectly. So that's what's being demonstrated with this picture of this isosceles triangle. We drew this line down the center where we folded the figure in half, and we see that each half matches up perfectly. And so this is a reflection symmetry. This folded line is called the axis of symmetry, or the line of symmetry. And so this line here would be the line of symmetry. Oops, actually, let's try this arrow here. So here are some examples of shapes that have reflection symmetry and some of their lines of symmetry. So as we discussed, or as we looked at in the previous example, this line here between this bisecting the unequal angle on this isosceles triangle is a line of reflection. So if I fold this shape in half, it matches up perfectly. I can also think of it as flipping over this line will result in the same exact figure, which is usually how I think about these reflections. If I look at an equilateral triangle, now where all 3 sides are the same, I can bisect any one of the angles and I get an axis of symmetry. So of course this vertical one still works. If I flip over this axis, or if I fold in half along this line, I have the same figure. And same thing if I bisect this other angle over here, the same exact thing happens, right? Because this is all of the sides are the same length, all of the angles are the same length, so it's no surprise that I can also flip over, bisect any one of these angles, and I have an axis or a line of symmetry. I can just fold it in half and I get the exact same pattern, or exact same shape. So there are 3 separate lines of symmetry on the equilateral triangle. If I'm looking at a rectangle, I have 2 lines of symmetry. This time they don't bisect the angles, because notice if I bisect this angle here and I try to fold the rectangle in half along this blue line, it won't match up perfectly. So that's not an axis of symmetry. However, I do have 2, and they are if I bisect each of the sides. So here if I bisect the long side and I fold this figure in half, it matches up perfectly, and same thing with bisecting the shorter side. And I fold over that line, everything matches up. With a square, I obviously have quite a few more, so I clearly have all the same ones I had for the rectangle, right? So I have these 2 lines of symmetry that I had for the rectangle. But I also have these other 2 lines of symmetry that I had that bisect the angle. So here now, if I bisect this angle and I fold in half, it does match up perfectly. And same thing, if I bisect the other pair of angles, it folds in half and matches up perfectly. So there are 4 separate axes of symmetry here. For the rhombus, I have two axes or lines of symmetry, each of them bisecting the angles. Um, but notice for the rhombus that I do not have an axis of symmetry anywhere else. So there are places that you might try to draw a line and get some symmetry, but if you actually put it into practice, it will not work. And same thing with the parallelogram. There are no lines of symmetry here. If I bisect either of the angles, things don't match up quite right. And same thing with either of the sides. Okay, so those are what we call reflection symmetries. It's one type of symmetry. There's another type of symmetry called rotation symmetries. So a symmetry is just kind of some sort of visual pattern. And we have some of these symmetries where we can do flips or reflections over a line. And then these ones are where I'm going to rotate about a point. So there is a point around which the figure is rotated less than one full turn so that the image matches the original figure perfectly. Okay, so the perfectly part kind of matters as we saw in the reflection piece. This point that we rotate about is called the point of rotation. So here's the kind of image that you should have in your head as you are rotating these figures. So if we start with this equilateral triangle, if I think of kind of moving, if I follow this lower right corner, it's moving up and up and up and up and up until once we get it into this vertical position, this lower right hand corner has now moved to the upper corner. We get the same exact figure again. And so this corresponds to a rotational symmetry. And we denote rotational symmetries by how many degrees that we have gone around the circle. So I think of like how many degrees this point has gone around a circle. So right there are 360 degrees in a circle to get all the way back. And so if I've done a third of them, I should be doing 120 degrees. So this one rotation corresponds to 120 degree rotation. Okay, so I can do, again, a similar thing with the rectangle, square, rhombus, parallelogram, and isosceles triangle. Here they're just asking me how many different rotational symmetries do I have. And it looks like if I take my rectangle, so here, this is handy, I can just kind of do it with, I think I can just do it with the figure here. So if I have a rectangle, I can, if I take some point in the middle of that rectangle, oops, get it right in there, and I rotate about that point, let's see if we can rotate about that point. Oops, is it gonna work? There we go. I have one symmetry at 180 degrees and another one at 360 degrees. So there are two rotations that get me back to the original figure, right? So I think it's most helpful if you can kind of color one of the sides or one of the pieces in your figure. I can't really do that and drag it all at the same time, but there are two rotations on that rectangle. For the square, we should have 4 rotations now. So let's see, if I look at drawing a square and I pick that point in the center of the square and I want to rotate this thing, now I can rotate 4 times. So let's try to do it. Oops. Not drag it, but rotate it. Let's see. 1 rotation gives me 1 line of symmetry. There's 2, 3, and then my 4th one brings me back to the beginning. Sorry about that. So there are 4 rotations for the square, should be 2 for the rhombus, 2 for the parallelogram, but only 1 for an isosceles triangle. Okay. So those are my 2 different types of symmetries. So at level 1 for analyzing figures using their components, Symmetry is going to be one of these things that I'm going to want to pay attention to. Students have now, at this level, moved beyond identifying shapes based on general appearance and are beginning to see components and parts of shapes. We can study components by investigating our surroundings. So one nice way of doing this is by kind of noticing things in the room or in your world, and then comparing them to, and then students can continue to investigate them by using dot paper. So this is kind of explained in more detail at this point in the text. But for introducing these different components and shapes and characteristics, the book likes to use a model that you might find in your classroom or is well known in our daily lives, and then try to abstract it and describe what that that component is, or that figure is. So here we have a model of a picture frame, and the top of the picture frame is what we're referring to as, or is a model of a line segment. And it's the set of points required to join, the set of points required to join 2 points in the most direct way, which sounds like an indirect way of describing something, but basically it's saying if I take 2 points, the line between them is the set of all the points that connects them in the shortest route, okay? And we think of the model of this as like the top of my picture frame. An angle, for an angle, they use the model of an open pair of scissors. The 2 line segments that start at the same point and go off in different directions give me an angle, right? Just like an open pair of scissors. A right angle is modeled by a vertical flagpole. An angle formed by 2 line segments that can be oriented, so one is vertical and one is horizontal. And as an example of parallel line segments, they talk about railroad tracks. So 2 line segments, which if extended to both directions, never meet, are what we call parallel line segments. Okay, and so then students can take this model and try to translate these different terms into something they can draw on one of these, like a dot paper. So here in picture A, we have a bunch of images of line segments, and in image B, we have a bunch of angles. So there are, of course, some terms that refer to different parts of these things. So at the end of a line segment, these terminating dots are called endpoints. And so this is the dots that end the line segment. And this point that where 2 lines meet to form an angle, this point is called the vertex. And then these 2 legs are called the sides of the angle. So just some helpful terms to suss out what we're talking about. Okay, so so kind of going through this activity and taking something in the real world and then trying to extend the abstraction with different examples on dot paper, it can help with the idea of length and measurement. So this is a good time to introduce length. As we can see in, especially in example A, we've drawn 3 different lines, and part of what makes them different is where they start and stop, so where their endpoints are, but also their length. So this can help us get a really precise meaning and understanding of measuring and of length. Okay. Great. So they've done the same thing with some of the different figures, giving nice models of things. So nice models for for the figures. So a scaling triangle is a triangle with three sides of different lengths. So all three sides have different lengths. And an example of this would be a bird beak. An isosceles triangle is a triangle with at least two sides of the same length. It could have all three sides the same length, but it has at least two. And so an example of that is a pennant. We have these two sides of the same length. An equilateral triangle has all three sides the same length, and a right triangle is one with one right angle. So it is possible to have some of these combinations of things. So for instance, any equilateral triangle is going to be an isosceles triangle, but not necessarily all isosceles triangles are going to be equilateral triangles. For example, this pennant that we've drawn here, or that we have here, is not an equilateral triangle. And it's at the next level where students can really start, at level 2, where students really can start thinking abstractly about, are all equilateral triangles isosceles, and are all isosceles triangles equilateral? Or can we have an equilateral triangle that's a right triangle? Which of these combinations are possible, and how to kind of group things differently and how they relate to one another. But right now we're really just picking out the components and their properties with things like side length and angles at this level 1 of identification. So we've done the same thing with quadrilaterals. So a parallelogram is a quadrilateral with two pairs of parallel sides. So we have this pair of sides is parallel and this pair of sides is parallel. The example or the model they give is a railing. Here, a rhombus is a quadrilateral with four sides of the same length. So all four sides have to be the same length, but not necessarily all of the angles need to be equal. Oh, I was right. Plural of rhombus is rhombi. I thought so. A rectangle is a quadrilateral with all four right angles, and a square is a quadrilateral with four sides the same length and four right angles. Okay, so again, at the next level, we're going to kind of start thinking at level 2, the student's going to start understanding the relationship that all squares are rectangles, but not necessarily all rectangles are squares. But right now, we're just going to start at this level, we're really thinking of just the components of these things, component distinctions. Okay, so two little tests that your book brings up here that are nice to be aware of are the parallel line segment test and the perpendicular line segment test. So they have these illustrations of how these two tests work, and I'm going to insert a little clip showing you how these tests work. But the parallel line segment test says, tells us whether or not two lines L and M are parallel. And basically, you take your two lines and you take your piece of paper and you fold it so that L folds onto itself. And then if M folds onto itself, then you know the two lines are parallel. Okay, if it doesn't, then you know that the two lines are not parallel. And it says M folds onto itself or an extension of M, meaning if you were to keep drawing M, it would fold onto itself.
Okay, so here is my explanation of the parallel line segment test. So here's an example. We have two lines and we want to test if they're parallel. So our parallel line segment test says fold your paper so that L folds onto itself. Okay, so I'm going to fold it like this so that L folds onto itself. It says then M and L are parallel if and only if M folds onto itself. So notice these look like two parallel lines. As I'm folding my paper so that L folds onto itself, M is also folding onto itself, right? So that it's overlapping. Here's an example of how it works when they're not parallel on this side. So here we can see these two lines are not parallel. There's L and M. We can kind of just visually test that they're not parallel. But my paper folding test says, okay, again, fold L so it folds onto itself. And notice now as I'm folding L so it folds onto itself, M is not folding onto itself. That means those two lines are not parallel.
So that's the parallel line segment test. And for the perpendicular line segment test, again, I'll insert a clip here in a second and illustrate what this image is doing off to the left. But it is telling us, we let P be a point at the intersection of two lines. So we have L and M, they do intersect at point P. And then we're gonna fold L at point P so that L folds across itself, okay? Then L and M are perpendicular if and only if M also folds along across. Or sorry, if and only if M is the line that you folded down, okay?
And now here's my explanation of the perpendicular line segment test. Okay, so we have two lines and they look like this, and we want to test if they are perpendicular. So here's L and M. They intersect at some point P. So what we want to do is we want to fold L at point P so that it folds across P onto itself. So again, with my line L, I just want to fold it so that it folds onto itself. These two lines are perpendicular if the line that we fold down is M. So it's a little hard to see, but hopefully you can kind of see that when I fold L onto itself, that crease is happening on M. Okay, and that means these two lines are perpendicular. An example of how this test shows me that two lines would not be perpendicular would be looking at these guys. So again, I have L and M intersecting at my middle point P, that's here. And at P, I'm going to fold L onto itself. And notice when I do that, M is not happening where the fold is. That means L and M are not perpendicular, okay?
Okay, so let's end this section by doing a couple of exercises from the end here just to kind of solidify some of these concepts. So for exercise 1, we want to, so 1 and 3, I want to look at, they're similar to some of the homework problems that are assigned. So for 1, we want to determine the types of symmetry for each figure and indicate the lines of symmetry and describe the turn symmetries. So for 1 here, it looks to me like we have some reflection symmetries. And specifically, if I draw a vertical line right down the middle, not super vertical, but let's get it, there we go. And I were to fold the paper in half here, I'd see that things match up perfectly if I can get right in the middle, which I can't do. Pixelation, so good. Okay, but hopefully you get the idea. Okay, so we have one, it looks like we have a reflection over a vertical line down the center. I can't do any of the other reflections because if I fold across any other lines, things aren't going to match up just right, right? So this one's not going to work. The diagonals are clearly not going to work. And I think, so we definitely have, for part A, we have reflection over the vertical line down the center. And we can also think of whether or not we have rotational symmetries here. So I'll imagine just putting a little dot right in the center of my figure that I'm going to rotate about. And notice there's no symmetry until I do a whole 360-degree turn. And so that tells me, I mean, every figure is symmetric if I do a 360-degree turn. That just gives you the same image you started with every time. There's nothing unique about that. So there's no symmetries here, right? If I try to do a half turn or a quarter turn, this does not match up right. All right, looking at figure B here, I think none of my reflection symmetries are going to work here. Definitely none of my vertical line. If I fold it over that, it doesn't match up right. If I draw a horizontal line, it doesn't match up right. If I do any of the diagonals, it just misses it. So there are no reflection symmetries for part B, but part B, I believe, does have a rotational symmetry. So again, let's kind of put an imaginary dot in the center of our figure, and we'll just kind of imagine turning it. And if I were to rotate, I think I can do a quarter turn and I will have rotational symmetry, and another quarter turn and I'll have rotational symmetry. And I think I can rotate it a quarter turn 3 times to have rotational symmetry. So this would be rotations of 1/4, 1/2, and 3/4 around would give me my symmetries. Or you can talk about it, or discuss them with degrees like we talked about before. So a rotation of a rotation of 90 degrees would be a quarter turn, a rotation of 180 degrees would be a half turn, and then a rotation of 270 degrees would be a 3/4 turn. But it's fine to just use these fractions. Either way, it's fine. Okay. So 3 here is talking about lines of symmetry. We want to know how many lines of symmetry are for each of these national flags. And notice that the colors should also be considered when we're thinking of these lines of symmetry, not just the shapes, I guess. So blue should match up with blue and white should match up with white, is what I think they're saying here. Okay, so we want to assume these flags are rectangular. So if I look at Argentina, notice if I'm looking at lines of symmetry, if I fold across a diagonal line, that's not going to work because the colors don't match up. But if I fold across a vertical line, that should be fine. So that's one line of symmetry. Same thing with a horizontal line, right? So we have 2 lines of symmetry for Argentina, the vertical one and the horizontal one. For Jamaica, I think we have the same ones, right? So we have the horizontal line and matches up fine, and the vertical line matches up fine. Again, I think if we do diagonals, it looks like we could do diagonals, but the problem is the colors don't match up quite right? Black's going to fold onto green, and green's going to fold onto black. So that will not work for us. So again, we still just have 2 of them for Jamaica. Okay, which of the following national flags have rotational symmetry? And what are the angles that we have here? So remember, this one's a little tricky because these are rectangular flags, so don't forget that. So it does appear that for the UK one, we could do just one 90-degree turn or a quarter turn, but it's not going to work out because we have the wrong shape of rectangle, right? It would be kind of like this shape. Oops, this shape, as opposed to this shape. So it looks like I can't do a quarter turn. I can do a half turn, so going 180 degrees, and then of course the full 360. So just one rotational turn of 180 degrees for the UK flag, and same thing with the Japanese flag for the same reason. It looks like we have more symmetry than that, but due to the fact that we have to keep it as a rectangle, that's not quite going to work if I do anything less than 180 degrees. Okay, one last exercise that's kind of similar to something that you might see in your homework. So given here are a variety of rectangles, sides with the same length are indicated, and right angles are indicated. So I wanted to make sure I talked about this. What they mean by that is when I have this one tick mark, it means that everything with one tick mark, all of those sides are the same length. So these three sides are all the same length. When I have, so these two sides, this two is the same length as this side because it has two tick marks. But this third side is not the same length because it doesn't have the two tick marks. And so on. So with F here, these two sides are the same length, but this one is not. And so on. And then, of course, the little box in the corner means that that angle is a right angle. Okay, so our first thing is to name the triangles that are scalene triangles. So remember, scalene triangles have all of their sides are different lengths. And it looks to me like there are just two of those, B and D, because all of the other triangles have at least two sides that are the same length. And then we want to name all of the triangles that are isosceles. So we want to name the ones that have two sides of the same length, or at least two sides of the same length counts as isosceles. So definitely C and F count, but so do A and E. Okay, because A and E have three sides of the same length, which means they have two sides of the same. And then naming the triangles that are equilateral, well, that's just A and E, because those need all three sides to be the same length. So notice that A and E are both equilateral and they're isosceles. And then name the triangles that contain a right angle, and that is just D and F. So notice that F is an isosceles right triangle. Okay. So activities like this can help us help students be able to see how these different properties relate to each other and how these different categorizations relate to each other. So now we can see, okay, I can have an isosceles triangle that is a right triangle, but I may not necessarily be able to have an equilateral triangle that's a right triangle. And in fact, I know that I can't, but these types of activities lead students to those questions and to be able to identify those themes and properties. Okay, so moving on in the next section, we're going to talk about relationships between shapes. So we're going to kind of, this is a nice leading into that next idea.